Hello everyone. In this video, I'll be discussing the problem that was put on Google group vlsidesignflow. So the problem was related to asynchronous checks in STA. First, let us look at the problem that was put. So in this problem, a timing report was put, which was obtained using the tool OpenSTA, and three questions were asked from this timing report. So the first was, what type of check is being performed in this case, right? So this question is pertinent because we see that the check is not performed uh, as in a conventional manner as set up and hold check on a flip-flop, but there is something called library removal time which is being checked. So constraint that is being checked is library removal time, and the check is happening not at the D pin of the flip-flop but some other pin, F2/RN pin. So the first question was, what type of check is being performed in this timing report? The second question was, for which kind of design entities can you expect this kind of check? And the third question was, why does this violation occur? So you see that there is a slack which is negative, right? It means that it is violated and there is probably a problem in our design which a designer needs to fix. So the short answer to these questions are as follows. So what type of check is being performed? So this is a removal check, right? So we'll be looking into what removal check is, and it is also a type of min check, minimum check, right? So we'll see what is a minimum check. And the answer to the second question, that on which design entities can you expect this kind of check? The answer is asynchronous pins of the flip-flops. So you can see that this pin is not the D pin on which the check is happening, but F2/RN pin, which is a reset pin of an or asynchronous reset pin of a flip-flop. Now, what is an asynchronous reset pin? We'll see. And then the third is, why does this violation occur? So this violation occur because the asynchronous reset signal arrives too early compared to the clock signal. Now, what does that mean? What problem it will create? We'll see subsequently. So these are the short answers, and now we'll be discussing these answers in more detail in the following slides. Now, let us first understand what are asynchronous pins and asynchronous behavior of a flip-flop. So if there are certain flip-flops in which we'll have some extra pins. So conventionally a D flip-flop has a D pin, a clock pin, and a Q pin, right? In addition to these pins, the flip-flop can have asynchronous reset pin or asynchronous set pin, or it is also known as preset pin, and reset pin is also known as clear pin. Now these pins are asynchronous. What does that mean? It means that when an asynchronous pin becomes active, the output can change irrespective of the clock signal. So let's take this RN pin. Now there is a bubble here at the input. It means that it is active low, meaning that if it goes from 1 to 0, it becomes active. So in a 0 state, it will become active. So whenever that happens, whenever the RN pin becomes low or it becomes 0, then at that time the output Q will turn to 0. It will not wait for the clock signal to come and then change to 0, but asynchronously or irrespective of the clock signal, the output Q will change, and that's why we call this reset signal as an asynchronous reset signal. Now, when the asynchronous pin turns inactive, meaning that the active part of a asynchronous pin in this case, because Rn is a negative active, so it is in this case it is active, and once it is active, it will again after some time after resetting, this pin may go back to the state 1, meaning that it becomes inactive. Now, uh, when the uh, asynchronous reset becomes inactive, so this is the inactive phase. So in the inactive condition, that is when it goes from 0 to 1, then the clock again regains the control, meaning that the flip-flop now again becomes or works synchronously, meaning when once the clock edge arrives, then whatever is at the D pin that will go to the Q pin. So when it becomes inactive, at that particular time, the clock regains the control. Now, to make synchronous behavior restored deterministically, certain timing constraints must be satisfied. Meaning that when it is going from active 0 to the inactive 1 condition, it cannot be done arbitrarily at any moment of time, right? It needs to follow certain constraints. Otherwise, the synchronous behavior will not be restored deterministically, meaning that we will not be able to know that whenever the clock edge comes, whether D is getting correctly produced at the output Q, meaning that if D was 0 and clock edge comes, we want that Q should be 0. If D was 1 and the clock edge comes, we want to that Q should become 1, right? So this is a deterministic behavior. But if the timing constraints on the asynchronous pin is not obeyed, or it is not followed, the timing constraints are violated. In those cases, this deterministic operation of the asynchronous pins or deterministic operation of the flip-flop will not be fulfilled. And what are these timing constraints? Let's look into that. So these timing constraints are known as removal checks and the recovery checks. Now, what is a removal check? So removal time is the minimum time after the clock edge that the signal at the asynchronous pin should remain active before it can be deasserted. So let us understand what this means. Suppose the clock is coming at this point, and initially the reset pin was active meaning that it was 0, and it is making a transition from active to inactive, it is going from 0 to 1. Now if if this transition is very close to the clock edge, if this 0 to 1 at the reset pin is very close to the clock edge, then the operation of the flip-flop will become undeterministic or bad, and we want to avoid that situation. So the removal time constraint is the minimum time after the clock edge, meaning that this is the clock edge. After this time, minimum time after the clock edge, that the signal at the asynchronous pin should remain active. So it should remain active within this period. It shouldn't change from 0 to 1 in this forbidden time, right? If it is making change in this forbidden time, then there is a problem, and this time is known as the removal time of the of the of the uh, uh, of the flip-flop, right, corresponding to this reset pin Rn. Meaning that if we want to deassert or remove the reset, we shouldn't do it very close to the clock edge. When the clock edge comes after some time, meaning that in this region, if it changes, reset pin changes from 0 to 1, it is fine. From here to here, it is fine. But if it happens in within this region, then there is a problem. Similarly, there is what is known as recovery checks. So recovery time is the minimum time that the signal at an asynchronous pin should remain stable after being deasserted before the clock edge. So what it means is that the asynchronous pin shouldn't be deasserted sometime before the clock edge, and that time is the recovery time. So before the clock edge also, it shouldn't change within this region. This is the recovery time, right? Now you can see that if you know, if you look into the setup and hold time, that requirement of the D pin, right? The removal and recovery are similar to that, right? So the removal check on the asynchronous pin is similar to the hold check on the data pin, right? So why it is same? Because it is appearing before after the clock edge, right? And the recovery check on the asynchronous pin is similar to the setup check, meaning that there shouldn't be change in the asynchronous pin sometime just before the clock edge, and this is similar to the setup check, right? Now if these checks are similar to setup check and hold check, the STA tool also makes the analysis in the similar manner and also reports us in the similar manner, right? So now let us look into the report and understand that why this violation came and what is the meaning of this violation in the timing report. So this is the timing report that I had shown, right? Now, corresponding to this timing report, this is the circuit, right? Now, in this timing report, we see that there is a clock, right? The clock at this point, which is going to F1 CK, that is at from this path, and then it goes to Q to this, and then it reaches the Rn of F2, right? So this is this is the launch path, right? And the capture path is from clock and F2, right? So this is where what is shown in blue, right? From clock, from here to here is the capture path, right? Now in this case, what is happening is that the removal check is failing on the flip-flop F2, meaning that the reset signal is coming too early, right? Too early after the clock edge, right? So if what is happening is that this is the launch path and signal is coming, and what is the delay it is encountering? It is the delay that is encountered is only between the clock and the Q pin, that is 0.0779. And what is the library removal time that is there so this time is there in the library. So in the library there is a removal time which is 0.1410 in the library, right? So if this is the clock edge and this is the removal time, that is 0.14, then the reset signal that should come at F2 should be after 0.14, right? That is what the timing window shows here, right? But when is it occurring, or when is it arriving at the reset pin? It is arriving at 0.0779, which is earlier than 0.14, and therefore there is a violation in this case, right? Now there are some other checks besides the removal and recovery checks that we have discussed. So there are some checks which are performed on the clock pin of the flip-flop. So what are these checks? The first is related to the minimum pulse width, right? So if my clock signal is like this, then the minimum pulse width checks that the pulse width that we have for the clock signal, it should be greater than some minimum which is specified in the library for the clock pin, right? and the other is minimum clock period check, right? So the clock period that we are giving at the clock pin, it should be greater than some minimum value that is specified in the library. If these checks are violated, then the flip-flop will not produce the data as expected. So to know more about the things that we discussed, you can look into this book, right? So these things are discussed in chapter 13.6. And for more questions related to VLSI design flow, you can join the group of this textbook, VLSI design flow. You can join by just sending an empty email to VLSI design flow plus subscribe at googlegroups.com. Thank you very much.